We live in a world of motion. People move, nature moves, and we build things that move, like cars and planes. But what about one of the most essential part of our lives and of life itself, light? How does light move? When you see things, you're actually experiencing light moving into your eye. But if a car was moving into your eye, you would definitely feel it. But you don't feel the impact of light on your body, so it must move in a different way than most matter. But why doesn't light push things like other matter? Does it have any momentum at all? The logical answer is no. You can't feel the sun pushing you down on a sunny day. Your brake lights don't seem to accelerate your car. But let's imagine this example. There's a flashlight floating through space, so there's almost no friction acting on it. If you turn that flashlight on, would the light push the flashlight in the opposite way that it shines? Well, the answer, in fact, is yes. Usually, when we think of motion, we think something has to have weight to have momentum. It's been discovered that particles of light, photons, don't follow this rule entirely. When they are resting, they have no mass, but they still have a small amount of momentum when moving. Just how small? Let's find out using this flashlight. It weighs about 400 grams and has 2D batteries totaling 3 volts and 12,000 milliamp hours. So using all of its energy, it creates about 130,000 joules. Using Planck's formula for momentum of a photon, we find the momentum of the photons, and multiplying in the 400 grams of the flashlight, we discover that the flashlight travels at 0.00108 meters per second. So that's very slow. How slow exactly? Well, if our flashlight wanted to travel from the corner of Arcola and Prince of Wales to Luther College High School, it would take 100 days. But this is assuming 100% efficiency, that all of the energy is turned into photons, while our flashlight probably has only about 5% efficiency. So realistically, it would be going closer to the incredibly slow 0.0000864 meters per second. Not surprisingly, this human invention is usually nowhere near as efficient as nature, like bioluminescent animals. Fireflies, unlike old flashlights, are incredibly efficient. In fact, fireflies boast almost 96% efficiency. So what if we created a new firefly that used its bioluminescence as a source of propulsion instead of its wings? Let's look at the energy output of this 15-gram firefly if it was flying through space so that it was frictionless and accelerated to 1 meter per second, which is the approximate top speed of most flying insects. If we use the same formula again, we find this little guy is using 4,700 joules to travel at that 1 meters per second, which is about 1 calorie. This is the number of calories in a grape tomato. So every time you, as a firefly, wanted to accelerate to 1 meter per second using your bioluminescence, you would have to eat an extra entire grape tomato already on top of your diet. This is entirely unfeasible when you realize a grape tomato weighs about 2 or 3 times as much as a firefly. It is impossible to fit enough energy in there to use photons as propulsion. No wonder a firefly like this never evolved. It would have to consume an unsustainable amount of energy. So we see that even with incredibly high efficiency, light-powered travel is all but useless. But that hasn't stopped scientists from theorizing ways to use it. Recently, many projects have tried to capture this momentum of light. One is the already tested solar sail, which travels by harnessing the sun's photons in a kite-like invention. Additionally, there's ideas for spacecraft that are propelled by photon engines or pushed by focused photon lasers on the ground, but both are too inefficient with current technology. It might take as much fuel as 100,000 rockets to create enough energy to get a photon rocket out of our atmosphere, which writes this off as an environmentally friendly idea. Even though it's small, the momentum can be significant. For example, the Viking mission to Mars would have missed the planet by 15,000 kilometers if the rocket scientists hadn't calculated the push of the sun on the craft. This force is always there around you and has significant effect on some objects. Light does push things, but like the photons themselves, that push is just very small. So the next time you're feeling blue on a sunny day, you can tell your friends that the sun's just weighing you down.